Today, we are going to be talking about secants and tangents again. And instead of talking about the angles, we're going to be talking about the line segments inside of our circles. And it turns out it relates to something we've seen before with similar triangles. We're going to look at three examples. The first two are kind of straightforward. The last one, a bit different, but you'll definitely get the hang of it. Let's get started. So what we're going to work on today is how can we use similar triangles to help with tangent and secant diagrams. Last lesson we talked about the angles. This lesson we're going to talk about the lengths of segments. Here A, B, C, and D in all of these diagrams just represent the length of line segments. This one only has 3, that's fine. And for our purposes, the line segments are going to go from one point to the other. For instance, A goes from here to here. It doesn't go beyond it. B goes from here to here. This doesn't have to be the center. This doesn't have to be any particular place. This doesn't have to be any particular place. So if we talk about this one first, these are two secant lines. They're intersecting inside the circle. And they actually make similar triangles. Reason being, if we were to draw this in and draw this in, well, this would be the same as this because they both have this arc. This would be the same as this because they both have this arc. So that means these two triangles are similar. And that gives us the really nice relationship of A times B is equal to C times D. And a nice little shortcut to see this is that they're all on the same line. A and B are on the same line, C and D are on the same line. Now, what this could look like is suppose this was totally not drawn to scale. 4 and 12, x and 6. If I wanted to find x, I would set up this equation. Well, 4 is just A, 12 is B, C is 6, C is x, and D is 6. Well, this would just be 48 equals 6x. So then we solve it out, and we're going to get 8. And that would be our answer, 8. This one, really similar process. We see two secant lines, just like this, except they're intersecting outside of the circle, not inside. That happens. The only difference is, we're going to say A times this whole length, and C times this whole length. So our formula looks a bit different. It's just going to be A times A plus B is equal to C times C plus D. Now, the reason that it has to be this is because we're doing the part times the whole, the part times the whole. I'm going to write that here. Part times whole is equal to part times whole. Alrighty, let's give this a shot. Why not? So if we knew this was, say, 2, and we knew this was 3, and this was 4, and this was x, we just plug everything in. So you'd have 2 times 2 plus 3, so 5. Then you'd have 4 times 4 plus x. Bit of algebra, you'll be able to solve. So that last example was kind of awful, so we're going to do a second one. This second example, you still see that we have a secant and a secant intersecting. Let's set it up. We're still going to use A plus B is equal to C plus D. And here we have A, B, C, and D. Let's just plug it in. So we're going to have 8 plus 12, 2 plus x. Well, that's going to be 8 times 20, 4 plus 2x. Well, that's going to be 160, 4 plus 2x. Subtract the 4, we're going to have 156 is going to be equal to 2x. Divide by 2 on both sides, we get 78 equals x. It's a larger number than we might be used to, but you can totally check it and see if it works. So you just saw our first two examples, and both of them really straightforward, using what we've seen before. Now we're going to look at a third one. It involves a tangent and a secant, as opposed to the last two, which were just two secants. You'll see the connection between this and the other two, and we'll go from there. Let's take a look. Let's take a look at this one. Here we have a tangent line, and we have a secant line. It looks different than the previous two because we only have 3 letters, A, B, and C. We don't have everything. But we're still going to use this idea of part times whole is equal to part times whole. And that's going to lead us to, well, this is the part and the whole here. So it's just going to be A times A. Or you can just write A squared. Now here my part is B, my whole is B plus C. So I'm going to do, well, B times B plus C, same as we did in the previous ones. Let's give an example here. Suppose this was X, this was 4, and this was 9. Well, then I'm just going to plug everything in. This is going to be X squared. This is going to be 4 plus 9. Well, that's X squared is equal to 4 times 13. So that means X squared is equal to 52, and I just do a square root. X is equal to the square root of 52. And as unsatisfying as that answer looks like, it's what we need. These can give you quadratics a lot. They don't always have to, but they can, so just watch out for that. Okay, so you just saw all 3 of our examples. Now, you're going to go on to Delta Math and give them a shot. Remember, you can take a look at your notes, you can ask me questions during office hours, or you can look at the supplemental materials, which I've posted below. If at any point you're confused about something during this video, post a question to it and I'll get back to you as soon as I can, or see me during office hours. Have a great day, folks, and I hope all is well.